Let's come up with some rules for approximating definite integrals. That's right, we're going to be approximating stuff, and we want to approximate in the same way. We want some nice rules for how we approximate definite integrals. Remember what the basis for approximating definite integrals is going to be and why we care so much. That second part of the fundamental theorem of calculus says that we can construct an antiderivative using a definite integral. And this is good because a definite integral can be approximating by thinking of it in terms of area. We're going to approximate definite integrals using area. We're going to be approximating definite integrals thinking in terms of area. The reason that we want to do this is that we can construct antiderivatives. And I said we can construct antiderivatives using the definite integral, that is using area to any degree of accuracy up to what our data will allow. So getting more data makes a better model, makes a better approximation. So let's think about the ways that we can do that. I'm going to give you a function, but I'm not going to tell you what the function is. I'm just going to give you some values for the function. I'm going to give you a set of data that we collected by observing this function. We'll start off at 80. Oh, whoops. I'm wrong at 9. 9 is the wrong one. I didn't want to drop 40. I wanted to drop 30. We dropped 30 twice. That's fine. So we don't have a lot of information about this function. One of the techniques that we had was that we assumed that the function was constant on a short interval. So one of our techniques for setting up definite integrals was assuming that the function is constant on short intervals. So what we want to do is approximate the integral from 0 to 12 of f of x to x. One way we approximated this, in fact, the way that we set up the Riemann sum is that we're assuming that the function is constant on short bursts for short bits. So if you recall, one of the techniques that we did was we assumed that f of x was constant for small changes in x. Notice that with this limited set of information, the smallest change in x we can get is 3 units, which is kind of a gigantic change. So for this data, our smallest delta x is 3. So I could look at this as with a delta x of 3, I can have n equals 4 The way we do this is we pick some value for the function on each of these rectangles to use for the height. So we're going to assume that the function is constant for small changes in x. In this case, the smallest delta x we can get is 3, based on the information that we're given. We have to choose some value for the function to be on each of these rectangles. And the way I have it set up into these 4 rectangles, I only have 2 choices. We only have 2 choices for the value of f on each of these rectangles. For this first one, from 0 to 3, I can choose 80. That's going to be on the left endpoint. Or 70 over on the right endpoint. So I have 2 choices on each of the 4 rectangles, left or right endpoints. This fits the model that we were using before. We are assuming that the function is constant on each of these 3-unit subintervals, these 4 rectangles that are 3 wide. And in that first rectangle, it's 80 on the left endpoint. It starts off at 80 and drops down to 70 3 units later, but we don't know what's going on in the middle. So we don't know what's going on in the middle. Somehow it's decreasing from 80 to 70. We got to pick a value from the function, so we'll go with 80. We'll use the left endpoint. And then let's do that for all 4 subintervals. That'll make an approximation that we'll call left 4. Left says use the left endpoint as the approximating value, and 4 is use 4 rectangles. So the left says use the left endpoint for the value of the function, and 4 says use 4 rectangles. So this first rectangle from 0 to 3 is going to have a value of function of the function is 80, and the width will be 3. For this next rectangle, I got left, the 70 is left and 50 is right. 70 is left. We'll use that for 3. We're just imagining instead of decreasing smoothly from 80 to 70 in whatever fashion it does, we're just going 80 and then just immediately dropping down and doing 70. Then we'll just immediately drop down and do 50 and so on. So it's going to be 150, 220 times 3. So there's an approximation. We don't have a lot of information, but based on the information we do have, it looks like this function is decreasing. And on each rectangle, we're using the highest value, the one on the left, since it's decreasing. And so this is probably an overestimate of the actual value. Spelled left wrong. This is probably an overestimate because from 0 to 3, the function decreased from 80 to 70, and I'm just using 80, the maximum value, the whole time. Now, if this function does something weird, like between 0 and 3, like at 1 second, or at 1, and when x is equal to 1, the function secretly jumped up to 100 and then back down, then I'm just not playing fair, right? We did a really bad job of collecting our data. So based on the data that we have, this function looks like it's decreasing. So it's probably the value we're looking for is something less. So notice that this 70 is the right endpoint of the first rectangle, but it's the left endpoint of the second one. This is the first left, and this is the first right, but the 70 is the second left. So we just calculated the left 4 approximation of the definite integral. You can probably guess what we're going to do next. The 4 still means use 4 rectangles. Now for each of the 4 rectangles, I'm going to use the right endpoints. I'm going to get an underestimate for this. I'm going to use the lowest value. So the first right is a 70, and we use that for that first rectangle. And then the second right is a 50. The third right is a 20. And the fourth right is a negative 10. I got this 3, so I'll factor that out. I got 140 minus 10 is 130. And the opposite happens. Since this function is decreasing and I'm using the end value of each rectangle, this is probably going to be an underestimate. Since f is still decreasing, right of any size is an underestimate. So it looks like our definite integral is somewhere between 390 and 660. That's not a very good range. It's a pretty wide range, but pretty wide range is better than no range at all. I've got an overestimate and an underestimate. I've got a value that's supposed to be somewhere in the middle. What are you going to do with them? Whether it's a good idea or not, what is pulling at you, what are you going to do with them? What's your natural inclination? It's somewhere between 390 and 660. What are you going to do with those two numbers? You don't want to say it, do you? You want to be like, oh, I'm not like those Brittany and Justin wannabes. I'll do something different. I just don't know what it is yet. But I know what your inclination is, because it's a natural inclination to connect these two with a line and split the difference. You want to think linearly because it's the default mode. As soon as you start doing math and you know that stuff can happen in the middle, the default mode for human thinking is, whether it's a good idea or a bad idea, is to just find an average. That's your default mode of thinking. Somewhere in the middle, let's average them out. And sometimes we do this average things when it doesn't make any sense whatsoever to do an average thing, right? But it's what we do. You can't stop it. I know you were thinking of it. If you tell me that you weren't going to average these two numbers, you're lying to me. I can smell it. I should have picked things that I can average without a calculating machine, but I didn't. So let me just grab my calculating machine. How much? 525. Thank you. Which is fine. We're looking for something in the middle. Let's just think about averaging them. How much was it? 525. Thank you. When we do this, this is actually a perfectly valid thing to do. But we need to understand the implications of what we've just done to make sure that it makes sense, right? We want to average things all the time. Averages don't always aren't always good representations of things. As long as we understand what we've done when we've created this average, then it's acceptable. Then I will find it acceptable in this scenario. So we got an average of 525. This changes the assumption that we made about what the function was doing as it's changing values. In our left and right assumption is we are making the function flat. We are assuming that the function is constant. When we find this average, we change that assumption. When you find the average of the left and right approximations, you're making the assumption that the function is linear on each of your delta x's. This changes our assumption. Perfectly valid thing to do, as long as we understand that this changes our assumption about f. In this case, we are assuming that f is linear on each of those intervals. So what you're doing here is assuming that the function is linear on each delta x. Instead of just saying 80 for 3 units or 70 for 3 units, 80 down to 70 linearly. You're making a line between those two. Let's draw a picture of that. Not of the whole thing. I can't draw the whole thing. So let's draw two of them at least then I guess. So what we're doing when we set this up is that we've got, the first thing we did was a left, we used the left endpoint. I used this value, and I said just use the left value for this entire 3 units. And then here's the left. And f of x is constant on each 3 unit interval. Constant, flat. We also did the right endpoint approximation. So for this 0 to 3, we made a rectangle and we said this is constant. But from the right, use the lowest value. When we find the average, we're making the function linear. So our average will be going from 80 down to 70. So we're actually changing the value. So we got to decide how it's going to be changing. And we're going to do the default human thinking and just draw a line. Remember, they call, we love you, Euclid. And Euclid be like, oh, I know. Because life is simple. If we use Euclidean geometry, everything's flat. It just works so well. And then from 70 down to 50, we're just drawing a line. Halloween's coming up, so I got to use the orange, the green, and the purple together. Feels very Halloweeny to me. Or Joker out. So we can actually see this line splitting the difference between our orange overestimate and our green underestimate. That box between those two, that is the difference between the left and the right. And we are literally splitting it with a line. So our assumption is the function is linear. Notice that the shapes we have are not rectangles anymore. The shapes are trapezoids. This makes sense because if you take 2 rectangles and average them, you get a trapezoid. That's why the trapezoid, the formula for the area of a trapezoid looks the way it does. It's 1/2 parentheses B1 plus B2 close parentheses H. It's just base times height, but it's the average of the two bases multiplied by the height. So we call this rule, when we average the left and right, the trapezoidal rule. Because a trapezoid is just an average of two rectangles. So when you average, if you have the left and right approximations, if you average them, you are finding the trapezoidal approximation. You can also write down the trapezoidal approximation directly by just calculating the area of a trapezoid. When we assume that the function is constant, we use the area of a rectangle, length times width. That's why we did the constant thing. If we average those two, that'll be the trapezoidal rule. And in that, using that rule, we are assuming that the function is linear. We are connecting from one end to the other in the simplest way possible with a line. Question? We can also calculate the trapezoidal rule directly. We don't have to start with left and right and find the average. But there may be a situation where we don't care about left and right. We say that is far too primitive for our purposes. I want the trapezoidal rule just directly. And so the area of a trapezoid is 1/2 B1 plus B2 times the height. It's just the average of the bases multiplied by the height. It's the average of the two rectangles the trapezoid sits in. No, I wanted to use the same ones as before. The trapezoid is the average of that red rectangle and the blue rectangle. Up here would be the B1, down here would be the B2, and this would be the height. So I'm going to calculate the areas of 4 trapezoids. add them up and divide by 2. That's the average. What we want to notice is that all of the values from our table get paired up. All the ones on the inside show up twice. The first one and the last one, they'll only show up once. Notice I've got 180 and I got 1 negative 10. The rest of them show up twice. So I got 270s, 250s, and 220s. So if we organize this a little bit better, I'm going to factor out the 3. And I'm going to factor out the 1/2. I've got 180. I've got 270s. I got 250s. 220s. And 1 negative 10. So when we see the trapezoidal rule summarized, we'll often see the delta x pulled out in front and divide by 2. The over 2 part comes in the trapezoid rule comes from the averaging that we're doing. That's that 1/2 in the 1/2 left plus right. We're cutting in half because we're doubling up on all of our measurements. And a lot of them just literally double up, but the first and the last one, they form a pair. So let me calculate this really quick, and we get 525 because I'm really fast at calculations. Any questions? Is everybody okay? So what we want to recognize, here's the TLDR. We started off with left and right. The N will represent the number of rectangles that we're using. We know we can improve our approximation by increasing N, but here we only could do a maximum of 4 because we had very little information to go on. But this is still based on our same assumption. We start off by assuming that the function is constant on small subintervals. Now we introduce the new thing. We looked at the function. We know the function is changing on each of those subintervals, but now we said it's changing in the simplest way possible. We're making a line. That's just 1 degree up. We'll make a line from one end to the other. That's going to geometrically create these trapezoids. So we're going to call it the trapezoidal rule. It's the average in left and right. And here's how we can calculate it directly without finding left and right first. So that one changes the assumption that we're making to assume that the function is linear from one end to the other. Next, we want to start improving the approximation. When we make approximations this way, we want to start improving this approximation by reducing the number of triangles that we need. That seems weird, but we'll see that tomorrow. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day. And thanks for playing.